Today we see cells, EMF, internal resistance. The electromotive force is work done per charge. It is independent of current. The energy generated or converted is independent of the current. Only depends on the charge. Normally work done per charge. W by Q. We write volt. Actually W by Q we should write epsilon. For the case of so work done equal to Q into EMF. We normally habituated to write. That's why confusion comes. Whenever there is a conversion, energy conversion from chemical energy to electrical energy, we have to rightly say EMF. We have to say not voltage V. That way problem comes. So when cell is converting charge, moving charge from here to here, it does work on every charge. It does work on every charge. It moves charge from because of this charge is accumulated on the terminal plus Q minus Q. It is accumulated. This energy conversion from one form of energy into another electrical form of energy is called EMF with the voltage as unit. On the other hand, the potential energy, the potential difference originates from the field created by the charge accumulated on the terminals of the battery. Let us take a cell. Let us move charge from terminal B to A. So what happens here when you are moving charge from B to A? The work is done on the charge. Work is done on the charge. Again, you see, I have not written Q into V. This whenever energy conversion, it is better to write epsilon or EMF E. That is a right convention to follow. So work done equal to Q into E. This is done conversion, chemical energy into electrical energy. This much energy is generated and converted to electrical form of energy. Because of that, charge is getting separated. From here, charge is moving, charge is accumulated on the terminal. Charge is accumulated on the terminal. So, during this process, some fraction of this energy appearing as a thermal energy. So, what we have generated and converted and minus the thermal energy appears as a terminal energy. So let us check. So the conversion work done, let us say 12 joule work done due to conversion, generation and conversion to electrical from 12 joule. Let us say fraction of thermal energy applies 2 joule. So remaining terminal we get only 10 joule energy. So this 10 joule appearing in the terminal results in potential difference. That is a point you have to understand that. So this thermal energy appearing in the battery, that corresponding to that resistance we are calling as an internal resistance. So we have this EMF minus thermal energy generated due to the current. It appears only if current flows equal to terminal potential difference we have. This is potential form. This is energy form. This is the difference between EMF and potential energy. So, whenever we are dealing problems, we deal cell only with whenever we have cell, ideal cell. This is ideal cell. Only no internal energy, no internal resistance, dissipation. So V equal to V here, When in the case of real battery, we have cell EMF and associated internal resistance. Then we have this formula V equal to terminal potential difference equal to EMF minus internal resistance dissipation potential drop due to internal resistance. This is ideal battery. In an ideal battery plus resistance. In an ideal battery, the EMF equal to potential difference. In the real battery, EMF and potential difference is different. When it will become EMF equal to V, when the current flow is 0 or the battery is open circuited, then only becomes V equal to E. So, in a real battery, when the battery is in open circuit, the EMF is equal to terminal potential difference. But in the case of ideal cell, the EMF is equal to potential difference always. That we have to understand. So, now we have voltmeter, we have battery. Then how to measure EMF of the cell? How to measure the EMF of the cell? A voltmeter cannot be used to measure EMF of the cell because it always draws some current. Then the question is, how to measure the EMF of the cell? So for that, first we will build a circuit. Then we do experiment. We will collect I versus V data. Then we plot the graph, whatever we got I and V. Then we interpret the graph for estimating EMF of the cell and internal resistance of the cell. So we will do the experiment. We will take one battery. This simulation is done in DC construction circuit, FIT Colorado.education. The battery, we set 12 volt battery. Normally car battery will have this 12 volt. And it will have typical internal resistance of 1 ohm. That also we have set. Now we are building up the circuit. We will connect an ammeter to measure the current flowing through the circuit. And we will connect a resistor, external resistors. This can be buried. So we will complete the circuit. Now, this value of resistance can be, external resistance can be varied. You can vary. So you can notice that color code is also changes. Color code also always changes. So this is our experimental setup. So we will set up 1 ohm initially, external load resistance, and we will connect voltmeter to measure the voltage. So for 1 ohm external resistance, 12 volt battery with 1 ohm internal resistance, we have 6 ampere current. 6 ampere. Now we will collect data. We will do experiment I versus V. We will connect I versus V. We will collect data. So first let us note this point. 6 ampere we get with 6 volt. 6 volt. Now we will change. We will change to 2 ohm. Then we get 4 ampere current. That we will note down we will record our observation. So we get 4 ampere with 8 volt. Now we will change our external resistance to 3 ohm. If you are changing 3 ohm, our current is 3 ampere with 9 volt. We will record our data. 3 ampere with 9 volt. Okay, now we set 4 ohm. We had 2.4 ampere corresponding to 9.6 volt. Now we will set 5 ohm. We get current of 2 ampere for 10 volt. Now we will set 6 ohm. We get 1.71 ampere corresponding to 10.29 volt. Now we will set 7 ohm. We get 1.5 ampere with 10.5 volt. Further we will set 8 ohm we will set. We get 1.33 ampere corresponding to 10.67 volt. It is sufficient. Our experiment is sufficient. We get sufficient data. So we will plot a graph. So we will plot a graph. We will plot a scatter graph. So the graph is coming like this. So you can see it is equal to it is a straight line. We can add a trend line. We can display the equation on chart. You can extrapolate forward and backward. So we have this. You see intercept. Now intercept is 12. So intercept is 12. So we have intercept is 12 means we have y equal to mx plus c. So we have here in the form of y equal to minus x plus 12. So c equal to 12. So our EMF is 12. So we have V equal to E minus IR. So we can rewrite E equal to minus IR Ri plus E. So slope is internal resistance. The intercept is our EMF. That is a point we have to understand. So that we are having, we are doing that. So this slope here, you can correct too much extrapolation here. One point you can reduce. Okay, not a problem is there. That we will see. So the intercept is 12. So the EMF of the cell is 12 volt. You see beautifully estimated from experiment. Of course we know the slope. We have assumed battery of 12 volt on 1 ohm internal resistance. Now we have only plotted IV. From this IV, we are extrapolating and finding the EMF. That is our experimental target. That we got it. That was, you see, Y equal to mx plus, the intercept is 12. So it is 12 volt EMF. Slope is minus 1, you see. So minus 1. So internal resistance of the cell is 1 ohm. So you have estimated, you have collected, you have done experiment, you have collected the data IV, you have plotted the graph, you have trend line you have added, you have interpreted Y equal to mx plus c, the intercept, Y intercept is EMF of the cell, the slope is internal resistance of the cell. That beautifully you have done. Slope you can identify from this slope also you can do. This slope also works. This slope also works. This slope also works. It is not, this is 2. This is 2. 2 by 2, 1. Minus 1. Okay, minus 1. Internal resistance is minus 1. So that beautifully you got the result. You beautifully got the result. So we have experimentally inferred the EMF and internal resistance of the cell. Now we will solve a board problem. The following graph shows the variation of terminal potential difference V across combination of 3 cells. In series to the resistor versus current I. Calculate the EMF of each cell. Okay. So we have the relationship V terminal potential difference equal to EMF minus IR, where R is the internal resistance. So this is of the form Y equal to mx plus C. So the intercept, Y intercept is nothing but total EMF. So here Y intercept is 6 volt. So 3 cells connected, 3 individual EMF multiplied by equal to 6 volt. So EMF of each cell is equal to 6 by 3 equal to 2 volt. So we got, because we used the fact that when they are connected in series, total EMF equal to E1 plus E2, E3. So we have 3 cells, identical we are assuming. Okay. Now next question. For what value of the power dissipation the circuit will be maximum? For this, what is we have to find out R internal resistance, total internal resistance. Okay, that is nothing but slope. The slope of the graph is internal resistance. So 6 divided by 2 is nothing but the slope. So R total internal resistance is 3 ohm. Now when the current power dissipation will be maximum? When we have internal resistance equal to or internal resistance equal to load resistance, then we have maximum power dissipation. So for this case now we want I equal to 3 divided by R plus R. So nothing but 6 divided by 3 plus 3 equal to 1 ampere. So 1 ampere we have. For current of 1 ampere, we have maximum power dissipation.